Hello everyone, my name is Ke Chen. I'm a doctoral candidate from the Technical University of Munich. It's my great pleasure to present my work, Real-Time Contact State Estimation in Shape Control of Deformable Linear Objects under Small Environment Constraints to all of you. Shape control of deformable linear objects with robotic manipulators are challenging due to the mismatch between DLOs' infinite degrees of freedom and the finite constraints manipulators can provide. To overcome this challenge, additional constraints have been utilized, typically provided by contacts from environmental fixtures. Here are three typical fixtures that have been widely used in manufacturing process: the pillar-like fixture, the channel-like fixture, and also the clip-like fixture and their corresponding contact processes. For preventing potential anomalies and enhancing robustness in these processes, reliable contact state estimation between the DLO and the fixtures are crucial. Especially, we find that the clip-like fixtures introduce a unique and dynamic contact process due to their own deformation, which can be described as follows. Initially, the DLO approaches and establishes contact with the clip's opening. Subsequently, as the DLO is pushed inward, the clip opens to let the object in. Once the object is inside the clip, the contact is detected unless the object moves further and collides with the rear part of the clip. In this clip fixing process, the contact force undergoes multiple stages of change, which brings challenges for accurate contact estimation. This has motivated us to propose an accurate real-time contact estimation of the DLO that can be used across various settings. We start with the formulation of the clip fixing process as a sequence of manipulation primitives. Each primitive consists of a feed-forward force controlled under an adaptive impedance controller. Initially, both robots grasp each end of a DLO segment. As robots stretch in the opposite direction, the DLO is also stretched until it becomes tense. Following this, robots guide the segment with a constant pushing force to establish contact with the clip. Upon contact detection, robots then insert the segment into the clip by applying a rising pushing force. The detected contact force will also rise as a clip opens. Once the DLO is fully inserted, the contact force drops suddenly and the robots stop applying forces. We also observed from our prior work that without an accurate contact estimation, problems can happen at different stages of this process. If the DLO passes over the clip opening, no contact is established between the object and the clip. If the DLO moves below the clip opening, it will be blocked by the fixture base. The contact force is maintained until the skew ends. If the pushing force is too much or not removed in time after insertion, the DLO will continue moving forward and collides with the clip. The contact force will rise again after dropping. We notice that these anomalies have different contact patterns and thus can be detected and avoided by accurate contact estimation. After that, we also analyzed in detail the force interaction after contact is established. Generally, the DLO is under a stretching force F stretch and a pushing force F push from robots, and a contact force FC from the clip. Taking only the components in y direction into account, the dynamics of DLO can be considered as a system that takes F push as input and generates outputs in the form of acceleration and FC. Then, inspired by the definition of stiffness, which is a ratio of the resulting deformation to the applied force, we define an indicator for describing the contact change, the rho C, at the rate of change of the resulting contact force to the feed-forward force. To capture the contact drops and rises, we make predictions about the future rho C from the history. The instant of a contact change is then detected when rho C deviates from the prediction. In the example below, we can see a case where rho C detects both contact detachment and re-establishment as it falls outside the confidence interval, but the vanilla contact force change rate fails to do so. Then we define another indicator, rho E, to detect whether there is a solid contact between the DLO and the clip. Rho E is defined as the ratio of the contact force to the feed-forward force, which initially equals to 0, and rises gradually until it is close to 1 in the process of contact establishment. Based on these two indicators, the ideal clip fixing process can be characterized by the contact force pattern, or more specifically, as sequences of contact establishment at detectment, denoted as zeta. Finally, we integrate the contact estimation method into the shape control process of our prior work to form an adaptive framework which could detect and correct anomalies automatically based on contact sequences. Now I would like to also show some real-world experiments and results. Firstly, we conducted experiments to evaluate the effectiveness and robustness of the contact change indicators. We compare its performance to two other intuitive indicators across various force rising patterns, positions, cable sizes, and clip shapes. The video together with the statistics show that the proposed contact estimation preserves the most robust performance across various settings. Last but not least, we evaluate also the performance of the enhanced shape control process. Here we see two front cam manipulators to attack the cable onto 4 clip fixtures. The first fixture has a vertical opening. In the first attempt, the robots missed contact with the fixture. By detecting this failure from contact estimation, they adjusted the skill parameters and gave a second attempt, where they succeeded. After that, they moved to the second fixture, which has a horizontal opening. At the following fixtures, the same procedure were repeated. In the first attempt, entry blockage problem was detected. After parameter adjustment, missed contact was again detected. In the third attempt, finally, the robots managed to insert the cable rightly into the clip.